Okay, so we were talking about non-adiabatic dynamics, and I just want to make a few more comments about that, about how do you do calculations of the dynamics, right, of trajectories when you have multiple electronic states that might be involved, and you can have non-adiabatic dynamics, right? So just to remind you, we're talking about a situation, oh, this marker is terrible. We're talking about a situation where, as a function of the nuclear coordinates, you have two different electronic states that are crossing each other. And if they interact, then they can give rise to two different Born-Oppenheimer potential energy surfaces. But at the intersection, there's a possibility that you can jump from one surface to the other, depending on the velocity, right? If you go fast through this intersection, then you have a chance to jump from one of the adiabats to the other. If you're going slow, then you'll follow the adiabat. Okay, and so I don't want to talk a lot about this, but I'll just introduce two methods that are currently in use. So this is actually a very difficult problem, and it's the subject of a lot of modern research in computational chemistry. But there's one method called surface hopping. And this method was introduced by John Tully. And in this method, you treat the nuclear motion classically on a potential energy surface. Right, so basically you just use Newton's equations of motion to calculate, based on the forces, based on the gradients of the potential energy surface, what are the forces on each nucleus, where are they going to go? And this is just like what we've talked about before, except every time you reach a seam of intersection, right, anytime you reach a point where two potential energy surfaces cross, you basically introduce a certain probability that you're going to hop from one surface to the other. So you allow a hop to another potential energy surface with probability calculated typically using Landau-Ziegler theory. Right, so we had this theory that we introduced last time. It should be the last thing in your notes from the last time, where the probability of making a hop from one adiabat to the other, it's given by an expression that has to do with the energy spacing, with the relative slopes of the two diabats, and with the velocity. Okay? And so this method has been very successful in treating cases where the system can really be described as being on one surface or another. But there's another approach that is necessary when you have a more complicated situation. And there it gets much more difficult. And the theory for dealing with dynamics that happens on multiple electronic surfaces simultaneously is very challenging. So one way of handling that is called Ehrenfest dynamics. And here you treat the nuclear motion as a quantum wave packet. Right, so you use the time-dependent Schrödinger equation to solve, the motion of the nuclei as a function of time, and instead of being a particle with a specific location, each nucleus is described as a wave function, right, a wave packet. And when this wave packet crosses through a seam of intersection, you can have some of the probability density go to one electronic surface and another part of the probability density go to another electronic surface. So your wave packet could be propagating simultaneously on both electronic surfaces. And so you have a very complicated situation. And that's all I'm going to say about that. I'm not going to go into any more detail about how to do that kind of calculation. So the wave packet may propagate on multiple potential energy surfaces simultaneously. Okay, any questions? So in surface hopping dynamics, you would kind of do many trajectories and choose which way to go based on a random number generator that generates a probability of going to one surface or the other, with probabilities that are weighted according to some theory for how likely it is to do a non-adiabatic transition. Okay, so that's sort of the end of this chapter. And there's a problem set on this chapter which I posted on the Blackboard page. It is going to be due before Thanksgiving. That gives you a week and a half. Usually I like to give 2 weeks, but I didn't want it to be due like over the holiday. So we can vote maybe at the end of class. If you want it to be due like by Monday after Thanksgiving, I'm open to that as well. We'll vote at the end of class. But you'll be getting the second problem set when you get back from Thanksgiving. So if you want a break in between, maybe it's nice to have it due. Okay. So we're going to be moving on to the next topic, which is photochemistry. And if you're following the textbook by Houston, this is chapter 7. Okay. And so photochemistry is basically what happens when you excite a molecule, usually to an excited electronic state. You give it a lot of energy, and it then has the opportunity to do various processes, some of which involve chemical reactions, okay, with the energy that it gets from absorbing a photon. So first of all, how do molecules interact with electromagnetic radiation, with photons, right? So you can describe, you can basically summarize interaction of molecules with light in terms of 3 different processes. You can have absorption, and that's when you take a molecule from quantum state 1 to quantum state 2. And in order to get the energy to go from a lower state to a higher state, it has to absorb a photon. Okay? And the rate of this process is described by what's called the Einstein B coefficient. So the rate is equal to this rate coefficient called B12 times the population of state 1 times the density of photons at the frequency required to have the photon energy to take you from state 1 to state 2. Okay? So this nu here, this is energy density . And the units are energy per unit frequency per unit volume. Okay, the second process is basically the reverse of the first process, and it's called stimulated emission. And that's when you have a molecule with population in state 2. The population falls from state 2 to state 1. And it's stimulated by a photon. But in order to have conservation of energy, the system has to emit a photon. So in addition to the photon that came in to stimulate the emission, the system has to emit another photon in order to fall from state 2 to state 1. Okay, and this process is the process that's responsible for laser light. So the word laser stands for light amplification by stimulated emission of radiation. And so if you have more population in state 2 than state 1, you can have a process where the light gets amplified because one photon stimulates an emission to make 2 photons, 2 photons make 4 photons, 4 photons make 8 photons, etc. Right? The process happens many times, and the emission that is stimulated is directional and it's coherent, meaning the emitted photon is in phase with the exciting photon. Okay, so this has a rate that's similar to this one, except the rate constant is called B21, and the probability is proportional to the population in state 2 times the photon density, or the energy density at that wavelength.
Professor,
okay. Yeah.
It is stimulated, so we have 2 photons in the final process, or is not just one with this, which is
well, one of these photons is the same one that came in.
Oh, okay. So it's 2 photons.
So one photon comes in, it stimulates an emission, and it stimulates the emission of a second photon that's in phase and has the same frequency as the first one.
Okay, so in principle, this photon which is stimulating this transition should have the same energy, but you have 2 photons, not one with the same.
Another way that you can think about this process is you have 2 photons coming out, but one of them looks like this, and one of them looks like this, so they cancel each other. So they're out of phase, so the amplitude cancels. But these ones are in phase, so the amplitude adds.
Okay.
But that's another way that you can think about it conceptually if you want. But usually I just draw it like this. The photon gets absorbed. But another way to think about absorption is you emit a photon that's out of phase with the incoming photon.
Because what I mean is if you sum the frequency, I mean, at least I see there is difference when you see the sum of frequency and just one photon. Because, for example, if I have a red light, they have a specific frequency. If I add double, multiply by 2, for example, so add red and red, I'm thinking have another color. Does that make sense?
No. We're just adding the amplitude. We're not changing the frequency.
Oh, okay. Yes, this is my question. I have two photons with
Yeah, you're not multiplying the sine waves, you're adding the sine waves.
Okay.
Okay, so then the third process is called spontaneous emission. And this process basically involves a molecule in state 2 spontaneously emitting a photon to go to state 1. So it's not stimulated by an incoming photon, it just is a spontaneous process that happens in the absence of electromagnetic stimulation. Okay? And so examples of spontaneous emission are fluorescence and phosphorescence. Spontaneous emission occurs in a random direction and with a random phase. Okay? So, in general, if you have a system in state 1 and it's interacting with light, then you can write the rate of change of the population, right? If you just consider two states, 1 and 2, and you can have a transition, then based on these rates here, oh, I'm sorry, I didn't write the rate for this one. The rate for this one is described by a different coefficient called the Einstein A coefficient. So this coefficient, we can call it A21. And then the rate is also proportional to the population of state 2. But it does not depend on the radiation density. Yep, exactly. So the rate of change in the population of state 1, then we could write an equation for that. So state 1 is going to disappear at this rate, right, at the rate of absorption. So we could write minus N1 times B12 times rho of nu. And state 1 is going to be generated by these two processes. So N2 times the rate of stimulated emission plus the rate of spontaneous emission. Okay, and by using thermodynamic arguments, right, for the, if you're at thermal equilibrium, what should be the relative population between state 1 and state 2, right? You can predict that using thermodynamics. And by setting the radiation density rho of nu equal to the blackbody distribution, right, so using a fairly simple to understand derivation, basically, Einstein showed that these coefficients are all related to one another. So they're basically all proportional to one another. So B12 and B21 are equal to one another, unless one state has a different degeneracy than the other, and then you have to multiply by the ratio of the degeneracies. But if you just have singly degenerate states, then these two processes have exactly the same rate. And so which one dominates will depend on which state has a higher population, right? If there's a higher population in the ground state, you have more absorption. If there's a higher population in the upper state, you have more stimulated emission. Okay, and the rate of spontaneous emission, it's different, but it's proportional to the B constant. So this one, if you do a derivation, you can find it's 8 pi h times the frequency cubed over c cubed times B21. So the spontaneous emission goes as the frequency cubed. That means spontaneous emission is very, very fast when you're talking about visible UV, ultraviolet, X-ray processes, but it's much, much slower if you're talking about low frequency processes. So microwave absorption and emission, infrared emission, right? These are very slow. So you can have excited vibrational or rotational states that live for a very, very long time. On the time scale of most experiments, they might never emit a photon. But if you excite a molecule to an excited electronic state, it might undergo fluorescence on a time scale of, microseconds, nanoseconds, picoseconds. It can be very fast. Okay. And this is these coefficients that describe the probability of a transition, right? The intensity of a transition. They're also proportional to the square of the transition moment if you're talking about a dipole transition. So dipole transition involves the electric field of the electromagnetic radiation interacting with a dipole moment of the molecule. And the formula for that is 64 pi squared. I'm not going to derive any of this. You can look in a spectroscopy textbook if you want to see the derivations. I can show you where to find them if you're interested. So these coefficients, they're proportional to one another, and they're also proportional to the square of the transition moment. And this transition moment, and I should also mention, there's also other units that you can discuss the intensity of spectroscopic transitions in terms of, so for example, you're probably familiar with absorption coefficients, right? Those are also proportional to these coefficients. You can talk about cross sections if you're talking about gas phase molecules. Those are also proportional to these quantities. And you can look up the, I'll put a little paper on the Blackboard site that gives the conversion factors between all these different quantities, if you're interested. Okay, so this transition moment, mu21, this is equal to the matrix element of the dipole moment operator connecting states 1 and 2. So in other words, dipole moment operator, right, a dipole moment is electric charge. It's a sum of all the electric charges times the position. So if you're talking about an electronic transition, it's due to an electronic dipole moment. So you have the charge of an electron minus E, right, which doesn't operate on the state. And then you have an integral of the state 2, right, which has a, let's say, part of the wave function describes the electronic motion, right? So the wave function depends on the electron positions and on the nuclear positions. Oh, sorry, V2. Right, so there's electronic and vibrational coordinates. And it's a function of electronic coordinates, little r, and nuclear coordinates, big R. And then you have the electronic position operator, right? That comes, so the dipole operator is E times the electronic position for each electron. And then this is operating on the wave function in state 1. And then you need to do this integral over all coordinates, including the electronic coordinates and the nuclear coordinates. Okay? And so in general, this is what this transition moment operator looks like, which describes the strength of an absorption from state 1 to 2. Under the Born-Oppenheimer approximation, so far we've assumed that the wave function, we haven't assumed anything about the form of the wave function, but under the Born-Oppenheimer approximation, we see that if we can apply the Born-Oppenheimer approximation, then you can separate the wave function into an electronic part and a nuclear part. Right, so psi EV of R comma big R, it's equal to an electronic part that depends on the electronic coordinates times a nuclear part that depends on the nuclear coordinates. And so using that approximation, you have that actually I have it here, I'll just write it here. So mu21 equals minus E times okay, so you have, if you can separate your wave function into an electronic part and a nuclear part, then you can also separate the integral into an integral over the electronic degrees of freedom times an integral over the nuclear degrees of freedom. And so this integral here, it's equal to what I would call so this first part here, I'll call this part 1, and then the second integral here, I'll call this one part 2. So part 1 is an electronic transition moment. You could call that mu electronic, connecting electronic state 1 and 2. And then the second part of this integral is a vibrational overlap. Right, so it's the overlap integral between the first vibrational wave function and the second vibrational wave function.
Is this first integral the Frank column integral?
The second one is the Frank-Condon integral, this one.
Oh, okay. The vibrational one?
Yeah, the vibrational overlap is the Frank-Condon. Well, the square of the vibrational overlap is the Frank-Condon factor.
Oh.
So basically, the transition is proportional to the square of this transition moment. So if you have a separable wave function, if you can separate electronic motion from nuclear motion, then it's equal to the square of the transition moment for the electronic transition times the square of the vibrational overlap. So this one squared, this integral squared is the Frank-Condon factor.
Oh, okay.
And naively, you might look at this integral and think, oh, well that should be 0 because it's the overlap integral between two different vibrational states, right? And vibrational states are orthonormalized. But actually that's not the case, because vibrational states within a particular electronic potential are orthonormalized with respect to each other. But if you compare the vibrational states in one potential and another potential, they're not necessarily orthonormalized, right? They're two different orthonormal bases. So let's talk about that in a little bit more detail in terms of the Frank-Condon principle. Okay, so basically the idea is you have a ground electronic state, maybe, and then maybe you have a electronically excited state. Maybe it looks like that. Maybe I'll draw it a little bit closer. Maybe it looks like that. Okay, and so you have different vibrational levels. So let's say you're starting in the ground state, so your vibrational wave function looks like that, and then you're doing a transition to an excited state. And the ground state of the excited state looks like that, but then there are excited vibrational levels. Maybe the second excited level the wave function looks something like that. Okay, and the Frank-Condon principle basically says that, like we talked about in the Born-Oppenheimer approximation, the motion of the electrons is much, much faster than the motion of the nuclei. So if you excite an electron, basically the electrons get excited to a new orbital configuration in a time that is very, very fast compared to the timescale of the nuclear motion. That means if this coordinate system describes the nuclear coordinates, and here is energy, that means basically you instantaneously go from one electronic configuration to a different one before the nuclei have time to interact, right? Before you have motion along the R direction. Okay, and so that leads to what's called a vertical excitation, meaning you go straight up on this diagram, right? So the nuclei don't move as you're exciting the electrons. And a consequence of that is that the probability of a transition is proportional to the square of this nuclear overlap. Because basically, so if you consider a transition that looks like this, there would be a very low probability of going from the ground state here of this electronic state to the ground state of this electronic state, because this one has probability density in this region, right? And this one has probability density that's shifted over. So this excited state basically has a longer bond length than the ground state. And so there's very little vibrational overlap if you take the overlap integral between this wave function and this one. But if you go to an excited vibrational state, this second excited vibrational state, maybe it has significant amplitude further over at nuclear coordinates that are close to the nuclear coordinates of the ground state wave function. And so if you take the overlap between this between this wave function and this one, then you might have a significant overlap. You'd have a much higher probability of going from here to the excited state, excited vibrational state. Okay, any questions about that? Okay, transitions between individual quantum states, in principle, should be very narrow, infinitesimally narrow, but they're never infinitesimally narrow because you always have broadening. You can have broadening of transitions, and this can be due to various different factors. You can have things like Doppler broadening. If you're talking about gas phase spectroscopy, this means the molecules all have a different velocity vector relative to the light. And if the molecule is moving away from the propagation direction of the light, then in effect it's feeling a lower frequency. But if it's coming towards the light, then it experiences more oscillations per second of the light, so it feels like the light has a higher frequency. And so depending on the speed, you could absorb light at a different frequency. That is the Doppler phenomenon. If you're in the condensed phase, you can also have effects such as chemical environment. Right? Maybe one molecule has a different solvent environment than another molecule. It might absorb, as a result, light at a different frequency. Or you can also have effects including lifetime. And so the shorter the lifetime, the broader the transition. And lifetime, that means the excited state in the transition, it doesn't live forever. It decays after a certain amount of time. And that could be due to things like emission, right? The excited state could emit a photon to relax to a different state. The excited state could do chemistry. It could, for example, photodissociate. The excited molecule could collide with another atom or molecule and undergo quenching, so collisional relaxation, etc. There's many possible processes. Okay, and lifetime broadening. Leads to a Lorentzian line shape. Which is described by the function, the absorption as a function of frequency. It's proportional to the width of the transition, right? Delta nu over 2 pi times a factor 1 over nu minus nu naught squared plus delta nu over 2 squared. And so this function, if you plot it, it gives rise to a peak that's centered at a frequency nu naught, right? Nu naught that's the value of frequency at which the denominator is a minimum, so therefore the function is a maximum. And delta nu is a width parameter. Delta nu here gives the full width half maximum. So if I plot this function, it's a Lorentzian, then in units of intensity versus frequency, it kind of looks like this. If you compare a Lorentzian peak to a Gaussian peak, a Lorentzian is narrower at the top and broader at the bottom in comparison with the Gaussian. And the full width half maximum here, this is the delta nu. And delta nu, if you have a certain lifetime that gives rise to broadening, then delta nu parameter here is going to be 1 over pi times tau, where tau is the lifetime of the exponential decay. Okay, another definition that we need to introduce is the quantum yield. So let's say you excite a molecule, and then it can do various processes. It could either return to the ground state by emitting a photon, it could do a photodissociation, it could become quenched by colliding with another molecule. The quantum yield, which is usually called phi, for a certain process, that's equal to the number of events of that process So for example, the quantum yield for fluorescence would be the number of molecules that fluoresce divided by the total number of photons absorbed. So for every molecule that was actually excited by a photon, what fraction of those molecules underwent a certain process? That's the quantum yield for that process. Does that make sense? Okay, that is all the notes that I want to give. We have just a few minutes. I'll show some slides. We might not get through all of them. We'll get through them next time. Oops. Thank you. Could you check that this is in the recording? Or adjust it if not. Where is my mouse? Aha. Okay.
Sabar dulu Pak.
Okay. Okay, so we've mentioned these different decay mechanisms, so we'll talk about them in just a little bit more detail. So if you have let's say you have an isolated molecule in the gas phase, if you excite that molecule using a photon, then by conservation of energy, the energy in the excited molecule is going to be conserved until it either dissociates, right, or emits a photon. However, in the presence of collisions, if you have collisions with other molecules, they can carry away energy from the excited molecule, and the molecule typically, in many cases, can vibrationally relax before emitting a photon. So, if you excite to a certain state, certain vibrational state of an excited electronic state in the gas phase, that amount of energy is always going to be maintained, right? If you have if you have a very low pressure, I would say in the low pressure limit. If you have high pressure collisions with other molecules, you can quench the vibrational excitation, and frequently what you observe is fluorescence from the lowest vibrational state. And in the condensed phase, this is also typically what you observe. You observe rapid vibrational quenching, and you would observe fluorescence from the ground state. Okay? And so a mechanism for quenching might look like this. So if you have a molecule in the ground state, it absorbs a photon. The rate is given by the Einstein B12 coefficient. You can make an excited state. The excited state can either collide with a quenching molecule or atom to make a molecule in some other state. Maybe this is a lower vibrational state. Or the excited molecule can emit a photon with a rate kF, which is the fluorescence rate, and that gives a molecule in the ground state plus a photon. Okay? And so if you assume that m is constant, and if you apply a steady state approximation to m star, you can actually derive that 1 over the fluorescence intensity is proportional to this quantity here. So if you plot 1 over the intensity of fluorescence versus the concentration of quencher, right, versus the pressure of quenching molecules, then you're going to get a linear plot where the slope is proportional to the rate of quenching divided by the rate of fluorescence. And yeah, so just to show you an example, at low pressure, you might have a situation where you can only emit from the state that you excited, right, because there's no collisions. And so at low pressure, you can look at the fluorescence spectrum, and basically if you excite a particular J state, that can only decay, or it can only fluoresce down to maybe 2 different states, one with a delta J of +1 transition and one with a delta J -1, giving rise to 2 strong lines. But if you add a quenching molecule, so if you add helium gas, this is data for the fluorescence spectrum of iodine molecule. If you add a quencher, then you can see a much more complicated spectrum where you have emission from many different vibrational states and many different rotational states. So you have emission at many different frequencies. Okay, if you take the same mechanism and if you assume that an initial amount of m0 is generated by a fast laser pulse, you can also do a time domain experiment where you look at the fluorescence decay as a function of time. And in that case, what this mechanism looks like, you start with an initial amount of m star and you watch it decay. And there's 2 parallel channels of decay. We talked about this mechanism in our kinetics class. The rate of decay is given by, there's an exponential, and the overall rate is just the sum of the 2 rates. So it's just like this parallel reaction process that we talked about in the kinetics class. And so the overall rate is given by this thing in parentheses. So if you look at 1 over the lifetime, that's equal to this rate. So if you measure the lifetime of fluorescence decay as a function of the pressure or the concentration of